Hello my friends and welcome back to the Today Machine channel. The combat supply ship Cantabria, designed and built by Navantia, a leading Spanish company in the military naval construction sector, is a groundbreaking vessel that goes beyond the traditional role of a logistics support ship. At 174 meters in length, the Cantabria is the second largest vessel in the Spanish Navy. Its size, however, is just the beginning of its impressive features. The ship is designed to provide logistical support to naval forces by supplying fuel, ammunition, food, and water to ships at sea, as well as performing humanitarian aid, medical support, and even marine pollution control operations. These versatile capabilities make the Cantabria a highly valuable asset for any navy. Navantia has equipped the ship with a double-hull design in the fuel storage areas, aligning it with the environmental regulations that will apply to all vessels, both civilian and military, by 2016. This makes the Cantabria the first military ship in the Spanish Navy to comply with these environmental standards, which are already in place for merchant vessels. The ship can store 9,000 cubic meters of fuel for other vessels, 10,000 cubic meters for aircraft, and 160 cubic meters of potable water, allowing it to serve as a floating fuel station and supply base for prolonged operations. The Cantabria is fully automated, thanks to Navantia's integrated platform control system. This system incorporates command, control, and communication technologies, enabling seamless interoperability with allied forces. The automation significantly reduces the ship's crew size, enhancing operational efficiency. One of the most innovative features is the SCBA, Sistema de Combate de Batalla Automatizado, a next-generation combat system developed by Navantia. This technology provides advanced combat and communication capabilities, making the ship ready for a range of naval operations. Additionally, the Cantabria is equipped with systems for degaussing, to reduce its magnetic signature, and NBQ, nuclear, biological, and chemical, protection, ensuring it can operate safely in various threat environments. What truly sets the Cantabria apart is its advanced at-sea replenishment system. The ship is capable of conducting resupply operations with other vessels, submarines, and aircraft, both during the day and at night. It features 5 supply stations and can refuel or resupply up to 3 vessels simultaneously while underway. The ship also supports vertical replenishment with helicopters, providing a critical supply link during naval missions. The Cantabria boasts a large flight deck capable of accommodating a heavy helicopter, with a hangar that can house up to 3 medium helicopters or 2 heavy helicopters. Additionally, it can carry and deploy 2 rigid inflatable boats, which are essential for rescue operations and rapid deployment in emergencies. One of the Cantabria's key strengths is its versatility in humanitarian and environmental missions. The ship includes a fully equipped hospital with the capability to perform telemedicine via video conferencing, making it a crucial asset in disaster relief and medical emergencies. This hospital, along with the ship's ample cargo space for humanitarian supplies, allows the Cantabria to play a vital role in international humanitarian missions. The Juan Carlos I, L-61, is a landing helicopter dock, LHD, named after the former King of Spain. This multi-purpose vessel was designed to meet various military and humanitarian needs, with a focus on amphibious assault, aircraft carrier operations, and logistical support. The Juan Carlos I was built at Navantia's Ferrol Shipyard using state-of-the-art technology and the expertise of highly qualified personnel. The ship's innovative design has attracted international attention, and its design has also been adopted by the Royal Australian Navy, which commissioned 3 similar units. Measuring 230.8 meters in length and 32 meters in maximum beam, the Juan Carlos I displaces 27,560 tons when fully loaded. Despite its massive size, the ship is capable of reaching a top speed of 20 knots. It is powered by a diesel-electric propulsion system, featuring 2 azimuth pod thrusters and 2 transversal propellers, providing excellent maneuverability. This cutting-edge propulsion system ensures the ship operates efficiently, with a range of 9,000 nautical miles at 15 knots. One of the standout features of the Juan Carlos I is its versatility, as it can be adapted to various missions. The ship has 11 decks, 4 of which are configurable to suit different operational needs. It is capable of acting as an amphibious assault vessel, aircraft carrier, or as a platform for humanitarian relief missions. The ship has a full-length flight deck of 5,440 square meters equipped with a ski jump ramp at the bow, 216 meters long and 32 meters wide, enabling the operation of short takeoff and vertical landing (STOVL) aircraft. Aircraft such as the AV-8B Harrier, Joint Strike Fighter (JSF), V-22 Osprey, New Hampshire 90 helicopters, and CH-47 Chinooks can be deployed from the flight deck. 2 aircraft elevators connect the hangar and garage to the flight deck, allowing efficient movement of aircraft during operations. In addition to its aircraft handling capabilities, the Juan Carlos I has a spacious hangar of 985 square meters, a light vehicle garage of 1,880 square meters, and a heavy vehicle garage of 1,480 square meters. These storage areas can accommodate a wide variety of military vehicles and equipment, supporting the vessel's amphibious assault operations. The ship also boasts a floodable well deck measuring 1,165 square meters, capable of transporting up to 4 LCM-1E landing craft and 4 Supercat fast landing craft, or alternatively, an LCAC hovercraft and 2 LCMs. The dock can conduct landing and amphibious operations even while the ship is sailing, providing flexibility in mission execution. Amphibious assault and aircraft carrier roles. The primary mission of the Juan Carlos I is amphibious assault, where it can deploy troops, vehicles, and supplies onto hostile shores. It can transport and support 1,435 personnel, including 247 crew members, 103 general staff, 172 from the embarked air unit, 23 from the naval beach group, and up to 890 embarked troops. The embarked forces can rely on tanks, vehicles, and helicopters stored in the garages, hangar, and well dock, giving them a high degree of flexibility during missions. As an aircraft carrier, the Juan Carlos I can operate up to 6 medium-sized helicopters, like the NH-90, or 4 large helicopters, like the CH-47 Chinook, simultaneously. The flight deck ski jump ramp allows the launch of short takeoff aircraft, such as the Harrier or Joint Strike Fighter, JSF, adding to the ship's operational versatility. hospital and humanitarian role. The ship is also equipped to provide medical and humanitarian support, with a 500 square meter hospital featuring state-of-the-art medical facilities. The hospital includes operating rooms, a trauma unit, and intensive care facilities, along with an elevator designed to transfer injured personnel quickly and safely. This makes the Juan Carlos I an ideal platform for disaster relief operations, where it can provide medical assistance, transport essential supplies, and house evacuees in modular containers. With its large size and advanced capabilities, the Juan Carlos I is also well suited for humanitarian missions, such as disaster relief or refugee evacuation. It can carry a significant amount of provisions, medical supplies, and vehicles, and is equipped to provide power, water, and healthcare services to civilians in need. The construction of LHD Landing Craft, LLC, for the Royal Australian Navy, RAN, is a significant project, with 12 units built by Navantia at the San Fernando Shipyard in Spain. Once the contract was awarded, Navantia followed a rigorous design and engineering validation process. This involved both the mission subsystem, which covers the design, construction, and testing of the craft, and the support subsystem, ensuring the LLC's operational readiness throughout their life cycle. The construction process began with cutting steel, followed by modular assembly, which ensured efficiency and adherence to the shipyard's construction strategy. After assembly, the craft underwent protective treatment in a blasting and painting cabin before the installation of systems like propulsion, navigation, and communications. The LLCs were built to high standards, with oversight from a classification society, which acted as an independent third party to certify that both design and construction met contractual requirements. Testing was conducted in 3 stages: workshop tests, port trials to verify system functionality, and sea trials to assess performance under various load conditions. These landing craft are designed to operate with the RAN's amphibious assault ships HMAS Canberra and HMAS Adelaide, which are modeled after the Spanish Navy's Juan Carlos I LHD. The LLCs are modern, versatile craft capable of supporting various amphibious missions, enhancing the fleet's operational capabilities. The 12 LLCs were delivered in groups of 4 and transported to Australia, adhering to the Australian Quarantine Service's strict protocols. Support includes activities like engineering, documentation, maintenance, spare parts, and staff training. These crafts are used to transport heavy equipment, including tanks, from amphibious assault ships to the shore. In particular, they are capable of loading and transporting a Leopard tank, which weighs 62.5 tons, during beach landings. These LLCs are similar to the LCM-1E landing crafts used by the Spanish Navy. The LCM-1E crafts, also built by Navantia, entered service between 2006 and 2008 and have a length of 23.30 meters, a beam of 6.40 meters, and a draft of 2.80 meters. They are equipped with two 809 kilowatts MAN diesel engines powering water jets, allowing them to reach speeds of 20 knots. These vessels are designed for landing heavy equipment, such as an Abrams tank or a combination of vehicles, over distances of up to 190 miles. As over-the-horizon (OTH) crafts, they can navigate beyond 20 miles from the coast and are equipped with advanced navigation systems. This capability makes them ideal for long-distance amphibious operations. The Leopard tank loading operation showcases the LLC's capability to efficiently handle and transport heavy military equipment, making them a crucial asset for amphibious assault and logistics operations. Engine production is a highly specialized and precise manufacturing process, involving multiple stages from raw material sourcing to the final assembly and testing of the engine. In modern facilities like this Navantia's facility in Cartagena, Spain, this process blends advanced technologies, high-level engineering, and stringent quality control to ensure that the engines produced meet the demanding requirements of both naval and land-based applications. This engine production unit is renowned for its manufacture of high and medium-speed four-stroke diesel engines. With a legacy dating back to 1947, the facility has a long history of excellence in engine production, delivering over 2,500 engines to clients globally, representing around 5 million horsepower. At the core of the production capabilities is its large foundry, which spans 7,000 square meters. This facility is equipped with the capacity to cast up to 60 tons of nodular gray cast iron and up to 20 tons of alloy casting, providing the flexibility to produce a wide range of engine components. Nodular iron, known for its strength and durability, is a common material used in casting large engine components, especially for applications that demand long service life and resistance to wear and fatigue. The foundry's advanced casting methods ensure that the materials used meet the high-quality standards required for high-performance diesel engines. Once the casting process is complete, the engine components move to the machining phase. The company employs flexible machining systems that allow for the precise fabrication of engine parts with high added value. These systems are designed for constant innovation and are equipped with self-monitoring technologies that ensure quality throughout the process. CNC machines are typically used to drill, bore, and mill parts to exact specifications, ensuring that the components fit perfectly within the engine assembly and operate efficiently. The use of modular machine tools and control programs with built-in inspection points ensures that each part meets exacting standards of accuracy. Navantia's assembly lines are designed to handle a wide range of engine types, including those undergoing repair or overhaul. Covering an area of 5,000 square meters, the assembly system operates with a modular design that ensures flexibility in production, allowing the company to meet tight deadlines while maintaining a high level of quality. The testing facilities are equipped to handle engines of different power ranges and speeds, with 8 test beds dedicated to propulsion engines and 1 to generators. These tests simulate real-world operating conditions, ensuring that each engine meets the required performance and reliability standards before it is shipped to the customer. Quality is a priority at every stage of engine production. Navantia's Quality Control Department implements a continuous improvement process that starts with the receipt of raw materials and ends with the delivery of the finished product. Advanced precision instruments are used to measure and verify that all components meet strict specifications. The department also conducts tests on materials and calibrates control equipment to ensure consistent quality across all production lines. The construction of Spectrum of the Seas, the first ship in the Quantum Ultra class operated by Royal Caribbean International, represents a significant achievement in modern cruise ship engineering. Built by the renowned Meyer Werft Shipyard in Papenburg, Germany, this ship is a further development of the Quantum-class ships, incorporating advanced design modifications and innovative features tailored to meet the specific needs of the Asia-Pacific market. The construction began with the symbolic steel cutting ceremony, which marks the official start of shipbuilding. This event occurred shortly after Royal Caribbean announced the ordering of a fourth Quantum-class ship, which would later become Spectrum of the Seas. Once the design and preliminary stages were completed, the keel was laid at the shipyard. A key part of this tradition was the coin ceremony, in which a coin was placed under the first block of the ship, a gesture believed to bring good fortune to the vessel and its crew. The ship was constructed using 74 individual blocks, each carefully designed to fit seamlessly into the ship's overall structure. Throughout the ship's construction, Meyer Werft applied cutting-edge technologies and engineering practices to meet the demands of building a next-generation vessel. The ship boasts an impressive length of 347.1 meters and a beam of 41.4 meters, making it a giant within the Royal Caribbean fleet. With a gross tonnage of 169,379, Spectrum of the Seas stands as one of the largest ships in the world and ranks fifth in the company's fleet by tonnage. A major milestone in the construction process occurred when the ship floated out from Meyer Werft's covered building dock. This marked the point where the vessel began to take its full form, and final touches such as the installation of its funnel cladding were made. Following this, the ship began its conveyance up the River Ems to the North Sea, where it underwent rigorous sea trials. These trials tested the vessel's seaworthiness, propulsion systems, safety features, and performance capabilities under real-world conditions. After successfully completing these tests, Spectrum of the Seas was cleared for delivery. The official delivery ceremony took place in Bremerhaven, where the ship was formally handed over to Royal Caribbean. This event symbolized the culmination of several years of design, engineering, and construction efforts, bringing the vision of a highly specialized cruise ship to life. After delivery, the ship embarked on its journey to Asia, where it was christened in China by two local celebrities in a grand ceremony celebrating its debut in the region. Designed specifically for the Chinese market, Spectrum of the Seas are massive, complex machines that rely heavily on robust engineering systems to ensure their smooth operation. One of the most critical components of a ship's engine is the crankshaft. The crankshaft, which converts the linear motion of the pistons into rotational energy to power the propellers, is central to the performance of a ship's main engine. On cruise ships, which often run for extended periods without interruption, the crankshaft is subject to immense stresses. For this reason, regular maintenance, timely repair, and eventual replacement of crankshafts are vital for ensuring the vessel's operational efficiency, safety, and longevity. At the heart of any diesel engine on a cruise ship, the crankshaft plays a crucial role in translating the reciprocating motion of the pistons into a rotational movement that drives the ship's propeller. In marine engines, which are designed for durability and efficiency over long distances, crankshafts are made from high-strength materials like forged steel or alloyed steel to withstand heavy loads. Cruise ships generally have large, slow-speed two-stroke engines that can operate continuously for weeks or months as the ship travels across oceans. The crankshaft's smooth operation is essential for maintaining the consistent power output required to drive the ship's propulsion system. Any imbalance, wear, or defect in the crankshaft can lead to catastrophic engine failure, putting the vessel and its passengers at risk. Therefore, it's critical to implement a rigorous maintenance regime that addresses the crankshaft's wear and tear. The impact of regular maintenance on crankshaft longevity. Regular maintenance of a crankshaft on a cruise ship is essential for preventing major malfunctions and ensuring that it performs efficiently throughout its service life. Crankshafts endure high levels of stress due to the massive loads imposed by the engine's operation. These forces can cause wear over time, even when the crankshaft is made from high-strength materials. Regular inspections and preventative maintenance can detect early signs of wear or imbalance, allowing repairs to be made before a failure occurs. There are several critical steps involved in crankshaft maintenance. Lubrication management. One of the primary causes of crankshaft failure is improper lubrication. The crankshaft rotates within the engine block on bearings, and the crankcase is flooded with oil to minimize friction and prevent overheating. Ensuring proper oil quality and level is crucial for the crankshaft's smooth operation. Routine oil analysis can detect contaminants or metal particles that might indicate bearing wear or oil degradation. Alignment checks. Over time, the alignment of the crankshaft can shift due to mechanical stresses or thermal expansion and contraction cycles. Misalignment can cause uneven wear on bearings and journals, leading to failure. Periodic alignment checks using laser-guided equipment ensure that the crankshaft remains properly aligned with the engine's other components. Vibration analysis. Vibration monitoring is another key element of crankshaft maintenance. As the crankshaft rotates, it experiences forces that can lead to vibration. High levels of vibration often indicate an issue, such as an imbalance in the crankshaft or damage to the bearings. Regular vibration analysis can detect these issues early, allowing operators to address them before they result in significant damage. Surface crack inspections. The crankshaft's journals and fillets, which are critical load-bearing areas, are prone to developing surface cracks over time. Non-destructive testing techniques, such as magnetic particle inspection or ultrasonic testing, are used to detect these cracks before they become serious. Regular inspections of these areas help identify potential weak points in the crankshaft that need to be addressed through repair or resurfacing. Repair procedures for crankshafts on cruise ships. When maintenance reveals issues with the crankshaft, timely repairs are necessary to prevent engine failure. When replacement becomes necessary. Despite rigorous maintenance and repair efforts, crankshafts eventually reach the end of their service life. The decision to replace a crankshaft is generally based on several factors, including the severity of wear, the extent of damage, and the crankshaft's overall age. Crankshafts experience cyclical stresses during engine operation, which can eventually lead to fatigue cracks. These cracks may begin as microscopic fractures but can grow over time. Once the crankshaft exhibits widespread fatigue, replacement is the only viable solution. Cruise ship engines undergo periodic overhauls, during which critical components are inspected and replaced if necessary. During these overhauls, the crankshaft is subjected to extensive testing. If the crankshaft is nearing the limits of allowable wear or if previous repairs have reduced its structural integrity, replacement is often recommended. In some cases, replacing an older crankshaft with a more modern design or material can improve engine performance and efficiency. Newer crankshafts are often designed to withstand higher loads or offer improved lubrication channels that enhance engine reliability. The safety and operational implications of crankshaft failure. The failure of a crankshaft on a cruise ship can have disastrous consequences. In addition to the engine failure itself, which may render the vessel immobile in open waters, the failure could lead to a chain reaction of damage to other critical engine components such as pistons, connecting rods, and bearings. On cruise ships carrying thousands of passengers, crankshaft failure poses serious safety risks. The ship's inability to move could leave it stranded in hazardous areas or subject to rough weather conditions. Moreover, such incidents can lead to expensive repair costs, potential environmental hazards from oil spills, and loss of reputation for cruise operators. Regular maintenance, repair, and replacement of crankshafts are therefore essential for mitigating these risks and ensuring safe and reliable operation. The maintenance process begins with regular inspections conducted by a dedicated onboard engineering team. This team is responsible for the daily operation and maintenance of the ship's mechanical and technical systems. Routine checks cover various essential areas, including engine systems, safety equipment, HVAC systems, and water treatment systems. Each ship's propulsion and engine systems undergo daily inspections to ensure optimal performance, including monitoring engine temperature, oil levels, and fuel consumption. Routine oil changes and filter replacements are scheduled to prevent wear and ensure reliability. Lifeboats, emergency alarms, and firefighting systems are tested regularly, and safety drills are conducted with the crew to prepare for emergencies, ensuring that safety protocols are well understood and followed. Preventive maintenance is a cornerstone of maintenance strategy. This proactive approach minimizes the risk of equipment failure and extends the lifespan of critical systems. Preventive measures include scheduled servicing, electrical systems maintenance, and sanitation checks. Equipment and machinery are serviced based on manufacturer guidelines and historical performance data, which includes lubricating moving parts, cleaning filters, and replacing worn components before they fail. Regular checks of the ship's electrical and electronic systems ensure reliability, including inspecting wiring, testing backup power systems, and ensuring that all navigational equipment functions correctly. Additionally, regular inspections of sanitation systems are vital for maintaining health standards on board, ensuring that the ship's water supply and waste management systems comply with health regulations. In addition to routine and preventive maintenance, Royal Caribbean schedules major overhauls through dry docking every few years. Dry docking is a critical process that allows for extensive maintenance and upgrades to be performed while the ship is out of the water. Key activities during this period include hull maintenance, propulsion system overhaul, structural inspections, and upgrades. The hull is thoroughly inspected for damage, and marine growth is removed. Anti-fouling paint is applied to minimize drag and improve fuel efficiency. The ship's propellers and rudders are inspected and repaired as necessary, ensuring that the propulsion system operates efficiently, which is essential for fuel conservation and performance. Structural integrity is assessed, including inspections of ballast tanks and other submerged components, with repairs made to ensure safety and compliance with regulatory standards. Dry docking is also an ideal time for implementing upgrades, such as installing new technology or renovating passenger areas. The company adheres to strict environmental regulations, ensuring that all waste management systems operate efficiently and effectively. The ships are equipped with state-of-the-art treatment facilities that manage wastewater in compliance with MARPOL regulations, treating both gray and black water properly. Additionally, innovations such as exhaust gas cleaning systems, scrubbers, are utilized to reduce emissions, contributing to the company's sustainability goals. These systems undergo regular maintenance to ensure optimal performance. The integration of technology into the maintenance process has transformed how it operates. Advanced monitoring systems allow for real-time tracking of equipment performance. Predictive maintenance techniques analyze data to forecast when maintenance should occur, reducing unplanned downtime and increasing operational efficiency. This technological advancement enables the company to address potential issues before they escalate into significant problems, ensuring smooth operations and passenger safety.